All right, welcome. So, having cooked up the first and second fundamental theorem over the past few sessions, we now are going to sort of take a step back from what we've done to sort of process the context. And so, today's session will sort of be two parts with a brief pause in between. The first part, we're going to look at the net change interpretation of definite integrals. So recalling the second fundamental theorem, suppose you've got a continuous function, well then you can determine the exact signed area between that function's graph and the horizontal axis using the antiderivative function, which is the consequence of that continuity, capital F of B minus capital F of A. And something sort of noteworthy to think about whenever you contemplate this expression is that the signed area between a function's graph and the horizontal axis really only depends upon two evaluations, a difference of them, but two evaluations of the antiderivative function, which when you talk about a change in something, right, it's, what's the change in my height comparing today to whenever I was 4 years old? You just take my height today minus my height at 4 years old, which is sort of an expression very much of this form, right? If you think of a variable changing with respect to time, let's do that. Maybe that's not too egregious of a thing to think about, right? Imagine this with respect to time. Well, here you just have something going on at time A and something going on a little bit time a little bit after A, something going on at time B. And so here is just a difference in an evaluation of a particular function at time B minus time A, which is exactly just a change, a net change at that. And so what if we take within context here, rather than looking at just a generic function f, what if we look at like a velocity function? Let's go back to thoughts that we've had previously about sort of a realistic context here. Well, if you were looking at the signed area between this function's graph and the horizontal axis, you would have some amount of positive signed area, which would be sort of like motion in one direction, and some amount of negative signed area, which would be motion back in another direction. It appears you have more motion in the initial direction, in the positive direction, than you do in the negative direction. So the net would be positive, and that is what would be articulated by this sort of change in capital F value. But now, what would the capital F be in this situation? Well, if you think about it, back to what you know from Calc 1, right? Take a velocity function and apply a derivative, and what do you get? You get an acceleration function. Go back one step. What function has a derivative which is a velocity function? Well, hey, that's a position function. And so now if you go backwards along here, you can talk about the antiderivatives of each. And now if you look at it from this point of view, the antiderivative of a velocity function is a position function. So if we are considering the signed area between our velocity function's graph and the horizontal axis from A to B, well, assuming our velocity function is continuous, which this one appears to be, and in general, the continuity of an object moving through space would be a continuous function. A velocity doesn't go from like 30 miles per hour to 50 miles per hour suddenly. No, if you go from 30 to 50, you go there, attaining every mile per hour in between. But yeah, look, this definite integral would be, via the second fundamental theorem, just the difference in the evaluation of the antiderivative function. But the antiderivative function to the velocity function is the position function. So this comes out to be just P of B minus P of A. And well, hey, check that out. That's the position at time B minus the position at time A. Much like I was talking about my height over time earlier, this is the position over time as it's seen. And well, this is really effectively just the net change in position from t equals A to t equals B. And in general, whenever you talk about a definite integral evaluates to just a net change in its antiderivative value. So the way that we can sort of interpret this antiderivative computation is just the net change in the antiderivative function from x equals A to x equals B. And if you think about x, the horizontal axis as being a time variable, which is often what is the case in like a practical real world situation, then you're sort of thinking of this net change as being the net change from A to B, which is essentially just the difference between the last value and the first value, which is, well, exactly what we've got here. So this rounds out sort of an overall step back, looking at the second fundamental theorem and observing the fact that the expression that results is really just a net change in antiderivative values. So hey, say you've got a velocity function and you're looking for the signed area between its graph and the horizontal axis, the resulting expression is just going to be the net change in position, which is, well, hey, a pretty nice thing to think about. And just, it sort of, well, echoes the context of definite integral with, through the lens of the second fundamental theorem. So having checked this off our list, let me pause the video and we'll come back for the second item on our agenda for this video. All right, so continuing forward, we're going to move on from the net change interpretation of definite integrals, which we had just seen, to a brief discussion about indefinite integrals. And I say brief because there's sort of only so much content here in a sense. But the idea is this. Look, if you're ever asked to evaluate the signed area between a function's graph and the horizontal axis on a given interval, which you invariably will be dozens of times this semester, it's really a two-step process. And the first step is, well, because, I mean, ultimately you're going to be trying to use the second fundamental theorem, because my gosh, it makes such simple computational sense of what is the area of some amorphously shaped region. And so, well, find the capital F function, right? And sometimes that's very straightforward because you just use the formulaic means that you are familiar with. Sometimes that can be a little bit more complicated because the formulaic means may require multiple steps. But nonetheless, find your capital F function. And once you find your capital F function, what do? You plug in B, you plug in A, and you subtract. Now, when it comes to those two steps, one of them is very much based in calculus, and the other is basically algebra that you could hand off to, you know, some well-trained seventh grader, right? Because finding the capital F function, that requires knowledge of calculus, knowledge of the rules of differentiation, to know the rules of anti-differentiation, and so on and so forth. Now, once you have the capital F function, plugging in B, plugging in A, and subtracting is actually, you know, really pre-calculus, right? That's essentially something that a middle schooler could compute without too much trouble. And so here is where the calculus lies, finding the capital F function. And so what if we just wanted to isolate that step of the process? Rather than plugging in the B and plugging in the A and subtracting, what if we just wanted to isolate the finding of the capital F function? Well, that is exactly what you do whenever you are given an integral without bounds. So here we're not given bounds, so we are not trying to compute an area or a signed area here. What we're trying to do instead is literally just find our capital F function. And we park a plus C on it at the end of it just to describe the antiderivative in general. So this is just the general antiderivative function, which really supplies the keys to the castle whenever it comes to computing the signed area between a function's graph and the horizontal axis. Computing a definite integral really requires evaluating an indefinite integral and then just plugging in B, plugging in A, and subtracting. And so just to look at a basic example so that we have context here, if you just saw an integral without bounds of x squared dx, this is simply going to be 1/3 x cubed plus c. All we're going to do is find the capital F function. And I say all we're going to do. That's actually the most important thing whenever it comes to computing the area between the function's graph and the horizontal axis, because once you have this capital F function, if you had happened to have had bounds, plug in the top bound, plug in the bottom bound, and subtract, right? So as another example, just to sort of round out the discussion and sort of put indefinite integrals into their appropriate context, if you had the indefinite integral of cosine x dx, note there's no bounds here, so we're not looking at an area. Rather, what we're doing is looking at the first step in the process if we were to be computing an area. Well, what function has a derivative of cos x? That, of course, is sine x. Throw on the plus c for a good form. Whoops, that plus c got knocked off the page. So I'll put the plus c right there, and, well, there we go. Now, you might say, oh, but that's just sort of isn't that taking a step backwards to antiderivatives? Well, in some sense it is, But from another point of view, it's using a notation related to the definite integral. C is the very function that allows us to assess the signed areas between the graph of cosine x and the horizontal axis between any two bounds. So we really get the keys to the castle for the cosine function and its signed areas by way of this sine x plus c. So what seems like a step backwards, because we're sort of breaking what previously was 2 steps down only into 1 and going back to just a discussion of antiderivative functions in their general form, is really actually giving us the isolating the step of calculus that is associated with the act of computing a signed area. Because, well, plugging in B, plugging in A, and subtracting is tasks for well-trained 7th graders, frankly. But nonetheless, this is really the content when it comes to indefinite integrals. And indefinite integrals need to be no more complicated than just finding the capital F function and moving on.